This is the third in our series of lectures on water as part of our UNA Europa Africa research project, and I see many familiar names from the first two lectures. And today I would like to welcome Professor Neil Robertson. He graduated from the University of Edinburgh, both with a BSc and then a PhD in chemistry. And after that, he worked in Europe at FU Berlin, then the University of Wales and Imperial College London before returning to the University of Edinburgh. And I think Neil had an office just opposite to mine for many years when I was in the School of Chemistry. He now leads research on new molecular materials and nanomaterials for solar photovoltaics, photocatalysis, electrical energy storage materials and devices, and has around 230 peer-reviewed papers in international journals. He is a fellow of the Royal Society of Chemistry and the president of the Royal Society of Chemistry Materials Chemistry Community. At Edinburgh, he is head of inorganic chemistry in the School of Chemistry, and he is the Dean International Partnerships for the College of Science and Engineering at the University of Edinburgh. And today his presentation is on photocatalysis for water treatment in rural India.
Thanks very much, Margaret. That's great. And thanks to the organisers for this opportunity to speak to you today. I'm going to share my screen and make sure this all works okay. So can you now see the screen? Yep, and the pointer. Okay, I think we're good to go then. And Margaret, you might notice I'm still in the same office. Okay, so thanks everyone for joining. As Margaret said, I'm going to talk about solar photocatalysis for water treatment in rural India. Rural India is where we've done a lot of collaborative work, but this could also apply to other similar rural parts of the developing world where water quality can be a significant problem. So just to reiterate some of the stuff Margaret was saying in the introduction, I'm a materials chemist. We work on new materials based on metal complexes, organic molecules and nanomaterials, and we apply these in electronic and optoelectronic applications, including semiconductors, solar cells, supercapacitors, batteries. But in this particular presentation, I'm obviously focusing on the optoelectronic properties of materials as applied to water treatment and photocatalysis. I'll start with the introductions and the acknowledgements. So this is work that we started about maybe 8 years ago, and was started by a PhD student called Guylan Odling. He was supported by the Criticat Doctoral Training Centre. The work was picked up by Victoria Porley. This is Victoria here. So she was supported by the Scottish Government Hydronations Programme. And more recently, Ayushi Arora, shown here, has taken over the work and has developed the work over the past few years, and she's supported by the E4 Doctoral Training Partnership, part of the NERC funding. We've also collaborated a lot with my colleague in engineering, Athalia Chachisomeon, and also some prior postdocs, Aruna and Brad. And most importantly, we've had a lot of collaborations with Indian Institute of Technology, Kharagpur, particularly Professors B.C. Maikap, Somnath Ghoshal and Pulak Mishra, who've massively supported our work in terms of the field studies in particular, and also some support from these other bodies here. So what I'm going to really do is go through a bit of a narrative of how we have progressed this work over the past few years, how we developed from materials chemistry into field studies and where that's taken us and what we need to do next. A bit of background, which I expect this particular audience will be very familiar with. Of course, clean water and sanitation is one of the Sustainable Development Goals. The WHO estimated this. These are figures from a few years ago, but they're still very, very much pertinent today. Around 850 million people are relying on unimproved water sources, predicting a global fresh water shortfall of 40% by 2030. And the Dow Jones Water Index just shows ever-increasing rise in the cost of clean water, which is also then a reflection of the scarcity. So this is a critical issue. Now, what we're interested in are developing parts of the rural economy in the developing world. So some of the most marginalized people who have the least access to clean water, where some of the biggest problems are, really areas of the world where large-scale infrastructure is unlikely to arrive anytime soon. Ideally, it will eventually, but it's expensive and difficult to provide good infrastructure across all these areas in the short term. Now, in that context, there is a technique which has been around for a long time, which is simply solar disinfection. So this is then the sun's natural disinfecting ability, used where water resources are unsafe and limited, and effectively it's just the UV component of sunlight directly killing bacteria. So it reduces the bacterial content, but there's a couple of problems. The rates are very slow, maybe 6 hours or longer of exposure of water and sunlight before there's a good enough effect. And also it does nothing for chemical pollutants, so particularly agrochemicals, pharmaceuticals, domestic waste chemicals, etc. So what we've been focused on then is the use of photocatalysis as a means of accelerating and improving solar disinfection. So using the same general philosophy, but adding a photocatalyst to speed this up. So the photocatalyst will then use light to initiate chemical reactions to speed this process up. So there's a paper here we published a few years ago, which outlined just where this sits in comparison with other technologies. And what we were trying to draw attention to in this paper is that there's been a lot of talk of photocatalysis for water treatment, often within large water treatment facilities as advanced oxidation treatment, like other advanced oxidation treatments. But the solar disinfection context has not been so widely explored, but actually it's a very good fit. And we feel that there should be much more use of photocatalysis in the solar disinfection context. So where we are here in terms of water treatment techniques, light-based rather than physical or chemical. SODIS is the simplest version of that with only light and nothing else, but for decentralized small-scale activities, we could add in a photocatalyst either in bottles or bags or a batch reactor or a flow reactor, lots of different ways of doing this, and I'll say more in a few moments about how we're going about it. So solar disinfection, to reiterate, requires UV radiation, at least 6 hours for water treatment, and that, however, is very cost effective and easy to implement because there's no infrastructure, no facilities, no maintenance, no engineers, nothing required, just a container, a transparent container that can be put in sunlight. But the problem is the waiting time still too long, and as I said, there's also only bacteria that are really affected. There's no treatment of chemical pollution. So if we include photocatalytic water treatment as an add-on to this, we can shift towards visible light, which means we can use more of the sunlight available. That gives significantly reduced disinfection times and can still be cost effective. But there is a missing link. There's not been an awful lot of field studies to back up what's already been done in research labs. Now, there are things available you can buy that basically do this job. So, for example, this company Puralytics will sell this water bag, a solar bag. So basically you fill up this bag and then you expose it to sunlight, and with some photocatalysis that will purify the water. So this is what we're discussing, what we're working on is not completely new. does exist, and it even exists commercially. But if you click through this buy now button, you get to purchase one of these bags. It's about £48 for one bag. So that's then maybe targeted towards walkers or adventurers or travellers who have some money at their disposal, but it's not really suitable for rural areas of the developing world where this would be prohibitively expensive. So more needs to be done to try to make this a technology that's available to a wider range of people. So here's the alert that some materials chemistry is coming up. I'll try to keep it as simple as possible, but I think it's important to try to explain what's going on. So here's the semiconductor photocatalysis. What we've got here is shown here is an energy level diagram. So energy is on the y-axis. This is the top of the valence band in the semiconductor, which basically means that's the top of the energy levels that are occupied by electrons. And this is the bottom of the conduction band, which are the energy levels which are empty. And when light shines on the photocatalyst, an electron can be excited from the valence band to the conduction band. So now we have an excited electron in the conduction band, so a high energy electron, and that's a very powerful reducing agent. It can add itself to some acceptor, labelled here as A, to become acceptor minus. We've left behind a hole in the valence band, a hole just being the absence of an electron. So that can then rip an electron off of some donor. So that donates an electron to the semiconductor and becomes donor plus. So what are these acceptors and donors? Well, we're in a water environment, and also this will be saturated with dissolved oxygen because we're in equilibrium with the air. So the acceptor will be O2. And that will go to O2 minus. Now O2 is kinetically inert. Thermodynamically, it's a powerful oxidizing agent, but it's kinetically blocked, which of course is a good thing, because if that were not the case, we would all just burst into flames because we are exposed to an atmosphere of oxygen. Once it's been reduced to O2 minus, that kinetic block is gone, and this then becomes a very reactive oxygenating species. It also forms other reactive oxygen species like hydrogen peroxide and hydroxyl radicals. Also here, this donor is most likely to be OH minus in a water environment, so that's then oxidized to OH radical. So again, a very highly reactive oxygen species. So these are collectively referred to as reactive oxygen species. So we take our contaminated water, which contains organic pollutant molecules and bacteria, expose them to sunlight in the presence of the semiconductor. That generates reactive oxygen species, which ideally will mineralize everything to carbon dioxide and water, kill bacteria, and destroy organic pollutants. So that's the general principle. We've been working for a number of years on this, as I said, and what we mainly do is materials chemistry. So we've been working on enhancing the photocatalyst. So why does the photocatalyst need enhanced? Well, the most commonly used material is titanium dioxide. It works well, but it has some limitations. First of all, it's white. You can see in this powder here. So it only absorbs UV light, which is less than 4% of the solar spectrum. So most of the available sunlight is wasted. It also has rapid charge recombination. Charge recombination is process 2 on this diagram. So the electron, after being excited, rapidly recombines with the hole and loses heat energy. So the energy is wasted. We want to avoid that. That's a second problem. And the third point is the powder would need separated. So we don't want to use a powder like this because we want to avoid any complex processing. We want the simplest system possible, so we would need to immobilize that powder. And over the years, we've reported a number of different strategies for improving these photocatalysts. I'm not going to go through all of this. Obviously, this is not the right audience for too much materials chemistry. But I will go through one or two just to illustrate the strategy and how we address these challenges. So I'll work through this one example just to show you. So the first thing is we can take a commercial titanium dioxide precursor, and doctor blading is a process just like spreading toast, spreading butter on toast. We can spread a paste onto a glass slide, heat it, and that will give us a titanium dioxide film, shown here in white on the left-hand side of the figure. We can then dip this into various solutions containing bismuth, containing iodide, sequentially, and repeat this multiple times, and that then builds up a film of bismuth oxyiodide on the surface. This is now an orange colour. So these are different numbers of dipping cycles. You can see the orange becoming more intense as we dip more often. Always nice to look at scanning electron microscopy pictures. So this scale bar is 1 micron, so these individual particles are maybe about 50 nanometers. So this is pure titanium dioxide, nanomaterial. The reason we use the nanomaterial is to get the high surface area, because the catalysis only happens at the surface of the material. So this will have about 1,000 times the surface area in comparison with a dense flat film. And this shows 3, 5, and 7 cycles of adding bismuth oxyiodide. And you can see the needles appearing that we guess must be bismuth oxyiodide. We don't have to guess, however, because we can look at the transmission electron microscopy. Here's an image here. You can see one of these needles. And with the energy dispersive X-ray spectroscopy functionality, we can show that bismuth and iodide are only present where this needle is, but the titanium and oxygen are everywhere. So we're growing these bismuth oxyiodide needles onto a titanium dioxide base. Not much more materials chemistry, I promise you, but a couple more slides just to illustrate again the key factors that are important. This is valence band XPS. All you need to know about this is it's showing you the energy level of that valence band, the filled levels where the electrons are. And this is titanium dioxide in the black squares. And when we add the bismuth oxyiodide, that shifts by about 1.67 electron volts. This diagram on the right-hand side is showing light absorption. When we have only titanium dioxide, that has an onset just over 3 electron volts, which means you need UV light to excite it. That shifts to lower energy when you add the bismuth oxyiodide, so now we can utilize some visible light. And on an energy level diagram, it looks like this. There's that valence band shift, 1.67 electron volts, the bismuth oxyiodide, and there's the band gap in the visible part of the spectrum. So now what do we have? Well, now when we absorb light, we can absorb visible light with the bismuth oxyiodide at lower energy. The excited electron will go down in energy, so it will hop onto the titanium dioxide. So we've done two things there. We have increased the light harvesting, because now we can absorb visible light, and we've separated the electron from the hole, so the recombination is much slower. And we've done the whole thing on a glass slide, which means we don't have a free-flowing powder. We have an immobilized catalyst that we can easily separate from the water at the end. So we've addressed all three of those key limitations that I mentioned earlier. Photocatalysis, let's start with some testing in the lab. So we can use model pollutants. So rhodamine B is a coloured dye. We can use that as a pretend pollutant and see if we can destroy that under photocatalysis conditions. Even better, 4-chlorophenol. This is now more representative of a genuine pollutant. This is a chlorinated aromatic molecule which is soluble in water. What we're seeing here is the degradation over time. So this is 0 to 80 minutes. And we're seeing a rate. The slope here represents a rate constant. And what we're seeing is that blue and black are control experiments with no catalyst and with titanium dioxide only. And then 3, 5, and 7 dipping cycles of adding the bismuth oxyiodide. We can see that 5 cycles is the best and gives a much enhanced rate of destruction of the pollutant compared with titanium dioxide on its own, using visible light. Here's the experiment here. The glass slide is dipped into a UV-vis cuvette. We shine the light onto that, and then every 20 minutes we can take this cuvette, put it into the spectrometer, and generate this signal of how much of the pollutant molecule is left. Again, with the 4-chlorophenol, you can see that compared with titanium dioxide on its own, shown in black, the bismuth oxyiodide modified material has a much faster rate of destruction of the pollutant. So that's working well. But putting something on a flat glass slide like that is not going to be very practical in the field. You can't carry around big glass window panes of catalyst. We wanted to put the catalyst onto glass beads. That's going to be more practical for use. So here's some glass beads here. Now, unfortunately, to make the catalyst stick, these are too shiny. You need to etch the surface with potassium bifluoride, which is an unpleasant, aggressive chemical. But for the moment, that's what we used. It gave us a rough surface, then could coat with a titanium suspension and have titanium dioxide coated onto the glass beads. We could then run some chemicals down a column over those beads to modify it with the second semiconductor. And in this case, what we got was bismuth titanate, titanium dioxide heterojunction. So again, this will be better for light absorption and better for charge separation compared with titanium dioxide on its own. Here's some photocatalytic testing runs. This is the 4-chlorophenol that we were testing. This is the percentage degradation of it over a number of different runs. You can see the repeated use causes the catalyst to get a bit poorer. However, if we then put it back in the oven to regenerate it, it jumps back up again. It drops away as you use it and it jumps back up. It actually becomes, effectively, it can be regenerated multiple times and doesn't show that much drop off upon repeated use. So it does seem to have long-term stable properties for long-term application. So that was with 4-chlorophenol. What about bacteria? Well, here's a untreated growth of a bacterial sample. If we carry out the photocatalysis with a titanium dioxide catalyst on its own, then much of that can be killed. And with the enhanced catalyst, we can kill nearly all of the bacteria in this particular experiment. So lots of colony-forming units upon the photocatalytic disinfection. So it certainly works for organic chemicals and it works for bacteria. So now we get to the first example of some field testing. So this is Victoria. This is March and April 2019. Field studies at the Indian Institute of Technology, Kharagpur in West Bengal. The IIT Kharagpur is the only major IIT which is located in a rural area. So before we started working with these partners, we did start some work with another Indian partner. And they would say to us, let's go to the village where we can work with the villagers and some experiments. It's 4 hours in the Land Rover. And clearly that put a bit of a barrier in place for running lots and lots of experiments. At IIT Kharagpur, they said to us, let's go to the village where we can do some experiments. It's just over that wall. So that was the difference. Because it's in a local area, they work regularly with local communities. The local communities are not surprised to see scientists walking around doing experiments. It's a good environment for this type of field study. So Victoria did various studies, 1 hour, 3 hours, 5 hours, control experiments with no catalyst, control experiments with unmodified catalyst, and then the enhanced catalyst, and got all sorts of results. She studied 5 different water sources. Now this brings me to really an important point about photocatalysis. This is not a technology that we're pushing forward as the solution to all water treatment problems. It has a very specific context. And the context we recognise is that it's very appropriate for situations where people are drinking untreated surface water. If you have other means of treating water, great. You probably don't need the photocatalysis. If you're drinking groundwater that's come up from quite deep probably doesn't have a lot of organic contamination, more likely to have a mineral problem, which the photocatalysis won't address. If you're looking at water that's polluted with minerals or polluted with metal ions, the photocatalysis generally won't address that. So it's not a solution for all contexts, but it can play a role where people are drinking untreated surface water, where the majority contaminants are either microbial, bacteria, viruses, etc., which can be destroyed because they're organic, or where the pollutants are agrochemicals, pesticides, domestic chemicals, etc., which are also organic and can be destroyed. So that's the context in which we're trying to think about this. So Victoria tried a village well, one in the village of Porapara, a village well just outside the boundary of IIT Kharagpur. Campus tap water, this is treated and should be clean, but because it goes through 80-year-old pipes, by the time it reaches the tap, it's not actually pure anymore. Tube well water, which again should be free of bacteria because it's coming from deep underground, but by the time it's being brought up and extracted through this apparatus, it tends not to be clean anymore. And some social water, or timed water they call it, which is available for a few hours a day. Again, this has been treated to some extent. So here's the bacterial colony counts. Here's the raw water before treatment. The safe number of colony forming units per mil, according to WHO, is 0. However, even the treated water, the timed water, and the campus water are showing hundreds, and the wells, the open wells, are showing thousands. So not good at all. After treatment, we managed to reduce this down to quite low figures. So the photocatalysis does work. In high sunlight, actually, even without the catalyst, it works to some extent. This is just SODIS. And in high sunlight conditions, even the titania works reasonably well. However, our modified catalyst worked the best. So we'll just flick through that. So that was the first field studies we did. That was in 2019. This is now Ayushi. Victoria graduated, got a great job, and Ayushi joined us, supported by the E4 Doctoral Training Partnership. And notice that now it's 2023 for the next field studies. So we didn't manage any field studies between 2019 and 2023. I wonder what could have caused that. I'm sure you all can guess. In fact, Victoria was in IIT Kharagpur in the beginning of March 2020, ready to do a second batch of field studies when she had to be brought home rather abruptly on one of the last flights. So, of course, everything was held back for a couple of years. Nevertheless, Ayushi managed to do some follow-up field studies in 2023, and in the intervening years, we managed to improve our catalyst. So now, using a different catalyst coated onto a different substrate, and the substrate we're now using are these recycled glass chips. So these are made by a water treatment company. Actually, they grind down recycled glass right down to a filtration medium. This is a company called Dryden Aqua, local to Edinburgh. So they grind the recycled glass right down to a filtration medium, but they give us some of it at this larger stage, and we can use it as a substrate for photocatalysis. So very, very sustainable and low cost and low impact because it's recycled glass. It's recycled anyway. And also we don't need to use aggressive chemicals to etch the surface because it's already rough. So we can attach our catalyst directly to this and then carry out our experiments. So enhanced support and enhanced catalyst, that's something we did manage to achieve during the intervening years when we couldn't do any more field studies. So now we can make a simple catalyst powder. This is a bismuth-doped titanium dioxide. Grind it up, make a suspension, dip in the recycled glass chips, take them out and dry them, and we get catalyst-coated chips, which is very firmly attached. We can add some additives to make sure that the catalyst is strongly attached. These letters here, RMSG, stands for reverse micelle sol gel. So don't worry about that. It's just the methodology by which we synthesize the catalyst. And again, here's the lab experimental setup. That's the one we used before with the glass slide, but using the glass chips, we can't use that. So we can put them into a dish and have the LED shining from above. In laboratory testing, again with 4-chlorophenol model compound, we focus on the purple here. This is the enhanced catalyst on the chips. It's working better than these other control experiments showing other colors, and also it does drop after repeated use, but again we can heat it and that regenerates the original functionality, and we use it again and then heat and regenerate, so it can be continually regenerated. Another control experiment, this is the glass chips on their own, shown in red, and they don't do anything to destroy the organic pollutant, whereas the catalyst functionalized glass chips do when exposed to light. So this is now a Yushi's field study last year. She considered 8 different locations. Sites 1, 2, 3, and 7 were pond water, not used for drinking, but used for washing, bathing, cleaning, and cooking purposes. Sites 4 and 6 were borewell water. So this is 4, this is 6, which is used for drinking. Site 5 is hand pump water used for drinking, hand pump, and then pond water. So she considered all these and looked at them all. First thing is, she studied standard water quality factors such as total dissolved solids, salt content, conductivity. All of this was in the parameters that are acceptable for drinking water. So because it's surface water, it's not suffering mineral contamination or any problems like that. But the problem is, again, microbial and organic contamination. So this time we studied total coliform and also E. coli specifically. So the most contaminated one of the ponds, site 3, in the thousands for total coliform, and the hundreds for E. coli. They should be 0 for drinking water, and actually should be 25 colony-forming units per mil or less, even for bathing or washing water, because those can also lead to contamination. So I usually focused on the very highly contaminated pond water and one of the borewell waters, which was also contaminated with total coliform. So you use the glass bead coated catalyst. That's the glass beads. Sorry, not glass beads, the glass chips, the recycled glass chips. This is coated with catalyst, positioned for treatment. And she also found that rotating the bottles really helps with mass transport. So the red one is rotated. You can see that the bacterial colonies come down much more quickly compared with no rotation, because if you don't rotate, there can be limits in mass transport. But she also looked at sunny versus cloudy weather. Now, what we found in general was that in very sunny weather, the photocatalysis and the enhanced photocatalyst is maybe not that necessary, because the SODIS itself already works reasonably well, to where you have maybe 700 watts per meter squared. But when it's cloudy, 80 watts per meter squared, that's when you need the enhanced catalyst. And in the cloudy weather, our enhanced system still worked pretty well, and definitely better than some of the control experiments. So this is where it becomes important. In sunny weather, then actually all of the catalyst and the controls can all work well. This is the pond water, and this can be massively reduced. This is no chips control. The green one is the enhanced catalyst, so dropping pretty rapidly in terms of E. coli and in total coliform. Reusability tests. Again, a slight drop off if you keep reusing the same photocatalyst, but if you carry out the regeneration just by putting the beads back in the oven again for a couple of hours, then it jumps back up to the original performance. So it's probably some residue on the surface which can be burned off in the oven every now and then. And this is, again, more reusability this time for the pond water. This was the borewell water. Again, good reusability. And the chips don't really change that much in appearance after use. The catalyst is still clearly there by eye. Okay, so that brings me basically to the end. This is the conclusions of what we've done so far. So this enhanced photocatalyst, sorry for the long complex name, but it's basically just a doped titanium dioxide, has shown up to 99.7% reduction of total coliforms in 2 hours with rotation every 15 minutes. That's much better than has been achieved with solar disinfection alone. It's shown efficient reusability tests up to 5 times, but then the efficiency can be regained after regeneration. So where are we now? Well, Ayushi was actually back in IIT Kharagpur in June this year. I don't have slides on this because she hasn't had time to write it up yet, but she was doing a field study which was much more focused, not so much on the physical chemistry, the water treatment, the catalysts, etc., which we now know that works. She was working with villagers, doing interviews, discussing with them, going through the methodologies to find out more about the practicalities. So she was working with a village to explore the cost, how much would they be willing to pay, the convenience, would they carry out this treatment or perhaps be demotivated if it's inconvenient. What sort of scale are these individual bottles the right scale to use, or would they prefer a centralized, larger facility where it's all done? The awareness and understanding of the condition of the water, associated health issues, etc. So that remains to be written up, but we have started that type of study to really try to progress this towards something practical and applied. Cost assessment is in progress, because we need to do a comparison with alternative technologies. So there's solar disinfection itself without catalyst, chlorination, which is in places, in some of the villages we've spoken to where there is any water treatment at all, it is by chlorination. They're provided with tablets, but then that has its own problems around generating chlorinated byproducts, which can have their own health effects. Boiling is of course very simple, but then also has energy demands and health issues around sources of fuel, etc. Filtration has problems around the end of life of the filters, etc., and the cost of that. So we need a cost assessment in comparison with alternative technologies, which is in progress. We're still double checking whether how well the catalyst lasts, how many times can you use it before some of it might be lost or some of it might become deactivated. And that's limited to then linked also to further reusability tests to understand how long you can use the catalyst before you really must replace it. What does that mean in terms of the cost assessment, etc. We also would like to study the degradation of chemical contaminants in the field. We've studied the degradation of chemical contaminants in lab studies. In the field, it's more difficult because often you're talking about very, very potent molecules at very low concentrations. So the analysis can be quite tricky. But that's where we are. That's the conclusions of where we've got to so far. And this is what's now ongoing in the next stage of our work. So I'll leave it there. Thank you very much for your attention. Happy to take any questions.
Thank you very much, Neil. That was a wonderful presentation and really, really interesting to hear about the developments of these catalysts over the years. I was just going to ask you, you were talking about the testing, the failure points of the catalyst. Are there any visible signs that the catalyst might be ready to be regenerated, or does it need to go back to the laboratory for testing?
There's no visible signs. There's no signs of loss of coating. There's nothing really to see. It really has to just be observed in the performance as to whether it's still performing. I think what we're trying to do is assume a certain time span after which it will need to be regenerated. So perhaps 2 weeks. So if it's been used for 2 weeks, it gets replaced by something fresh and gets taken away for regeneration on a cycle. But you can't see. You just have to test it and see if it's still working.
Yep. I think Julian has his hand up.
Yeah, thanks very much. Thanks, Neil. That was very interesting. I have a few simple questions, nothing on materials. Just as a quick follow-on, as you said, it sounds like there's some biofilm or some coating on it, which is reducing the efficiency. So when you regenerate it, what type of temperatures do you use in an oven?
Before 500 degrees.
And have you tested it lower? Because ultimately, I think to use this, it would be something that they could regenerate themselves, I guess, if possible.
Yeah, I think we have discussed trying that. It's kind of awkward to do because you'd have to do a lot of tests to generate a lot of catalyst that's no longer working as well as it used to then try them all at different temperatures to then repeat that a few times to make sure it's working. So it's a bit laborious.
It's not exciting, no.
Yeah, but we do recognise it's important. So yeah, it is something we have to do.
Okay, I just have one or two follow-up as well then. The bit that I missed, like how is this then used in practice? Do you take a bottle and just put some beads in it?
Yeah, and leave it in the sun for 2 hours, rotate it every 15 minutes.
And then drink it. That's great.
Drink it. Well, we don't drink it at the moment.
Oh yeah.
We'd have to fill in a lot more forums if the people are actually going to drink it.
Well, that's the question I did have as well, and I know there's a couple of questions that in terms of the ongoing future work which are very interesting. You don't know if there's any catalyst lost, as in does it give anything in terms of the quality of the water? Obviously, you haven't tasted, so you don't know if it influences the taste. But is there? I mean, I assume you've done some analysis to see if there's higher concentrations of titanium or something else within the water afterwards.
Yeah, we have done a bit of that. We need to do more again, but we have chosen things which are inherently non-toxic or very low toxicity. So titanium dioxide in nanoparticle powder form, it may be of some concern for inhalation, etc. But in tiny quantities in water, I mean, titanium dioxide is a food additive in some cases.
Yeah. You're right.
Bismuth is present in Pepto-Bismol. So that's again a medicine additive that's ingested already. So we've chosen elements that are already of very, very low concern. And yes, you're right, we do still need to do further work to verify that there's absolutely no quantity of any concern leaching into the water.
Yeah, and of course that's important for the longevity. Okay, now my last question. I mean, of course, I think it's a very interesting result that on a sunny day, no additives or anything, and you can still reduce coliform counts. Is that common knowledge there? I mean, is that widely used by them? Do they stick water in a bottle and stick it on a window for 5 hours or whatever, or do they care? I mean, do they drink directly from these water sources, as in the social time water or some other drinking water?
Yeah. So it gets quite complicated. So first of all, about up to 5 million people around the world have used solar disinfection. So that's just putting the water in the sunlight on its own. The fact is, even in some places in certain parts of the world, there's been historic religious rituals of blessing the water, etc., which has probably been a way that has actually became a thing in a non-scientific context in kind of older civilizations. So solar disinfection does work. There are issues with it. As I said, you need to have quite intense sunlight and you need to have it for quite a few hours for that to work on its own. And it'll do nothing about any contamination other than microbial.
Yeah.
The other thing is that where agencies and NGAs, etc., have introduced sodas deliberately, it tends to die away again when they've left. So it's difficult for people don't stick with it necessarily once the NGA's left town. That's been a recurring problem, and it's maybe partly because it's too simple. People don't really feel like they've done anything, or it's too much hassle, or they're not making a link between time off work through illness,
Yeah.
and the fact that they might prevent that. So in some ways, the solar disinfection might be too simple. I've always wondered if having a product, a thing, actually would make people do it more, because it just feels like
Yeah.
they're
If
adding
you just
something.
if you just gave them glass beads and said, look, these work,
Yeah.
and it may encourage that continuous use then of them. So I mean, in this village then, beside your main study area, I assume it's they drink the treated water, the social water, or is it bottled water?
So there's different villages we've done some experiments in. Some drink the treated water, the social water, which is also contaminated, or the hand pump water, which is also contaminated. In some villages, they get chlorination tablets from the government, but then that also has a cost to the government, because they're handed out for free, and has side issues around chlorinated organics, generating chlorinated organics in the process, which can have long-term health issues as well. And in some places, they don't treat the water at all. They just drink it straight from the well.
Thanks very much. Very interesting work. Thank you.
Thank you.
Okay, I see another hand up. So I think it's Roa.
Yeah, thank you. Thank you for the interesting presentation and this very promising research. I have a question about the water turbidity. Is it affecting this process? I don't know, maybe you mentioned that before I joined the meeting, but I was working in Sudan in many places where this is a real issue, and in many places we used to work in water harvesting facilities, so the turbidity is very high. I'm wondering if this technology could be effective even the water, the surface water is very turbid, or the turbidity rate is very high.
So where we've worked, the turbidity has been low, and it's not been a problem. I would expect that if the turbidity is high, it would be a problem, because the methodology depends upon light penetration to excite the catalyst. So I think if you had highly turbid water, you'd need some kind of settling or pre-filtration or something. Otherwise, it would not be as effective.
Okay, yeah, I can see that. Thank you.
So I see that we have 2 questions in the chat. So the first of these from Daisy, does the photocatalyst water purification system need to function specifically in small water bottles? Is it possible to spread the beads in a pond to purify the water there?
So it doesn't have to be in a small bottle. In fact, one of the outcomes of the discussions and interviews with the villagers was that they would find that a bit inconvenient and too much personal hassle, and that they would prefer something more at a village scale or a multiple household scale with a larger container, that they didn't have to constantly do stuff with themselves. So larger containers may be better, but then you have to be mindful of mass transport. It can't be too deep, otherwise water at the top will never reach the catalyst. So it'd have to be quite large, flat type container to have a large surface area to catch sunlight. Would it work in a pond? Potentially, yes. I think we have discussed with collaborators a potential project along those lines. That's all I really want to say in the moment. But in principle, yes, you can have a passive system that just sits in a pond, but that then has to be more engineered in some way to be kind of stable in that context, and to be functioning and not fall apart, etc. Just be contained in that context. So that's the part we've been discussing with some collaborators.
Okay, and then the second question online, and then I'll come back to Julian. So the second question in the chat from Ronald is: would photocatalysis work optimally during winter season? What would be TRL of the technology?
So in the winter season, of course, it will be less rapid, but this is then where the photocatalysis becomes important. So the solar disinfection by itself, as we've shown, is fairly poor in cloudy conditions, so that would also apply to winter conditions. However, with a catalyst, then that's not so bad. I think it's not so much winter that's the issue, maybe more rainy season. So in the rainy season, where there really isn't so much sunlight at all, then there could be a limitation there. That's a possibility. Although, as I say, with the catalyst, it's better than with no catalyst. TRL, the technology, well, obviously, it depends on the context. So Puralytics are already selling it for people who can afford to pay. So the technology works. It's more about whether we can make it work in a context that would benefit people who have, at the moment, very little other water treatment options, or sometimes no water treatment options. So it's more about TRL in a certain context.
Thank you. Now to Julian.
Yeah, sorry, I just remembered there was another question I wanted to ask. Your substrate is these glass chips made from recycled glass, and you said there's a company that does something with water that uses them and grounds them down. I just wondered what they use them for.
So Dryden Aqua are based just outside Edinburgh, and they grind. I think they get about a third of all the coloured glass bottles in Scotland, and they recycle them, grind them down into a fairly fine glass material. They do some kind of secret surface treatment, and then it's a water filtration medium, which they use for drinking water in some contexts, and also in swimming pools and aquaria. So they're a very successful company. They're expanding overseas with this particular activated filter medium. They call it AFM. So if you want some, you can buy some from Dryden Aqua.
You haven't compared your media to theirs?
Well, it's different. So they need a system, because they're doing a filter system with well, I suppose it's like a sand filter in a way. It's more technologically advanced than that, but it's a silicon oxide glass material, surface treated. So it's like a sand filter, effectively, that they're making, and that requires an engineered system. Whereas
large scale.
Exactly, what we're looking at is something that could be used in areas where there's no maintenance, there's no technology, there's no engineers to repair anything. Something more passive.
Yeah, I just wondered if you could take some of their stuff and stick it in something like a Brita filter.
Well, so they have developed a product, because they have a subsidiary or a sister company that works on developmental aspects for different parts of the world, and they have developed a solar-powered, fairly straightforward filtration backwash system that they've worked with in Bangladesh, for example, for water treatment. So I think it's just about horses for courses. They're working in a context where there's maybe a deficiency of water treatment, but there is some capability to run and maintain a filtration system if they can provide it. Whereas we're considering the context where that's absent, and that people really just need a very, very simple, low entry level passive technology that doesn't require maintenance. So yes, what they're doing is really important, but it's aimed in a slightly different context from what we're doing.
Thanks. Yeah, no, it's clear. Yeah, it's personal versus engineered. Thanks.
And there's another question in the chat. Is there a specific quantity of catalyst required to effectively treat a specific volume of water? That's from Claire.
Depend upon the time and the level of contamination and the intensity of the sunlight. I think I can't remember exact masses, but we were using tens of grams to treat a couple of litres of water, but most of that weight would be the substrate rather than the catalyst. So but yeah, we've been choosing a particular amount of catalyst, but effectively what we've been doing is making having enough catalyst to form a single layer at the bottom of the container. Because there's no point in having multiple layers, the light won't reach the stuff at the bottom. So the right amount of catalyst is to have a single layer sitting at the bottom of the container.
Thank you. And then just one question for me. The chemical contaminants, so you studied chlorophenol in the lab. Do you intend to do more laboratory testing, and do you have a set of chemical contaminants or types of contaminants that you would test next?
We have done some work in the past on actual pharmaceuticals to try to follow what's happening there. I think there is a question around, if you don't completely mineralize something, what do you end up with? Probably bits of organic molecules that might still be harmful. So there is some importance in considering that, and considering how actual example pharmaceuticals or example agrochemicals will be broken down by the photocatalysis, what's the time scale, etc. And then there's also the question around forever chemicals, PFAS, highly fluorinated molecules, and whether photocatalysis is perhaps one of the methodologies that would be suitable for destroying these, because they're the particular problem for removal from the environment.
Yeah, thank you very much. That's great, and I think we're just about out of time, and we've asked Neil so many questions, and I think there's a really great wide-ranging discussion following on from your excellent lecture. So I would just like to thank you again for giving that lecture today, and thanks to everyone for attending and for all your contributions. And I will really look forward to the next lecture in the series in a few weeks' time. Thank you very much.
Thank you.